Hey y'all, my name's Kalen, and today we are going to be talking about epigenetics. Now, epigenetics literally means on or near genetics. Now, that name is important because epigenetics, unlike a lot of other things involving genetics, does not involve a change to what your DNA actually is. You're not going to get a point mutation. You're going to be working with the same set of base pairs the whole time. There's no frame shift. Everything is staying the same. What's changing is how tightly the DNA you have is wrapped around your histone. So let's recap that for a sec. You have your DNA, represented by this strand, in its double helix form. There's about 6 feet of this in each of your cells. Now, that's going to be pretty difficult to fit if you just leave it loose like that. So what does the body do? Well, the body's smart. The body has these proteins called histones. And it's going to loosely wrap your DNA around those histones. And that's important because if the DNA is too tightly wrapped, then it can't be coded for. The RNA can't reach it. It can't be transcribed. So if the body wants to shut off a piece of the DNA, it doesn't want to code for a certain gene, but it doesn't want to get rid of that gene either. It's going to engage in something called DNA methylation. When DNA methylation occurs, you get the gene wrapped really tightly around each of those histones. Now the fascinating thing is, your environment can cause that DNA methylation to occur. Things that you experience physically will change how your DNA is expressed, and that can be passed down to your children. So Professor Meany from McGill University studied this in rats in a study maternal care associated with methylation from 2006. And he found that if a rat child does not experience extensive physical affection in its upbringing, then the gene that codes for an estrogen receptor associated with affection gets methylated. So to be clear, more methylation means lower expression, which means that now in terms of this rat child's DNA, because it did not experience a lot of affection, it now is going to be less affectionate with its own children, which is incredibly sad. This is true for humans as well. If you are not shown a lot of affection as a child, you are less likely to be affectionate with your own children. But it doesn't have to be that way, because they found, let's represent this little oval is a lonely rat child whose mother didn't show it lots of love. And over here, we have a high affection rat mother whose own mother showed it a lot of affection, and now it has a very high representation of that estrogen receptor gene, which in turn means low methylation. The DNA is loosely wrapped. Now let's say that this mother fosters the lonely rat child from the low affection mother. That affection that the rat mother shows the rat child is going to demethylate that estrogen receptor gene, which means that now the estrogen receptor gene is going to be more expressed, turning this rat child from a low affection rat to a high affection rat. Now this can also carry through in terms of environmental trauma and danger, which is fascinating in terms of its connection to natural selection. So in a study called Lamarck Revisited, Professor Seif exposed rats, or mice actually in this instance, to the smell of acetophenone and then shocked the mice. So now they came to fear the smell of acetophenone. Now what's fascinating is that their children also feared the smell of acetophenone, even though they had no reason to, other than the fact that their parents had experienced that trauma, but how could they know about that? Well, they knew about it because the gene that coded for an olfactory receptor for acetophenone was demethylated. So again, demethylation means that the gene is more expressed. So before being exposed to the acetophenone and the electric shock, the DNA of the parents was pretty tightly wrapped. They weren't really looking out for that particular smell. But after being shocked, that DNA, it's going to be the same diagram over and over again, that DNA gets demethylated, gets looser, it's more likely to be coded for, and that demethylated DNA for that olfactory receptor gene got passed down to the children. And then finally we have a study that discussed humans. So I'm sure y'all are aware of the horrible trauma associated with the Holocaust, and one of the effects of the Holocaust on the people that directly lived through it was a higher methylation of the FKBP5 gene, which is associated with PTSD and other stress reactions. Now what's fascinating is that the children of those people actually have a lower methylation or higher expression of that gene than the average population, which basically indicates that because their parents experienced trauma, their genetic codes adapted to be more prepared to deal with stressful traumatic situations, and thus upped the expression of the FKBP5 gene by lowering the methylation. So to recap, the Holocaust methylated the FKBP5 gene in the people that directly experienced it. So it is less expressed. It's traumatized them. That gene is less capable of regulating stress reactions. However, the children of the people that experienced the Holocaust saw their FKBP5 genes demethylated and more expressed, which have made them, to an extent, more capable of dealing with stress reactions. So to recap, the environment changes how tightly your DNA gets wrapped around those histones. The tighter it's wrapped, the less that gene is going to be expressed. The more loosely it's wrapped, the more that gene is going to get expressed. And this wrapping can be passed from generation to generation, as seen particularly in the Scythe example with the mice. Thank you so much, and I hope you all have a great day.